I'm Ron Pressler. I work at Oracle in the Java Platform Group. That is a group that develops OpenJDK. And today, I'm going to talk to you about Project Loom. Project Loom is a new OpenJDK project, which means it is developed separately from the JDK. It is not yet a JDK feature. In the future, it will become integrated. In the meantime, you can download early access builds of a JDK with Loom at this address and give them a try and send us feedback on this mailing list. Because I'm going to be talking about a future project, you shouldn't really trust anything I say. Okay, so Project Loom is about concurrency, and I want to spend some time on explaining what it is. Perhaps it's best to start with explaining the difference between concurrency and parallelism. So parallelism is when we have a single job to do, a single task, and we want to do it faster by exploiting multiple processes. And when we do something in parallel, the performance measure we're interested in is how long it takes us to do this single task. And that is the latency of that task. Concurrency is something else entirely. Concurrency is when our application needs to manage multiple different and independent tasks simultaneously. Normally, those tasks come externally. A good example for this is a server. Now, when we speak of concurrency and performance or scalability, the measure we're interested in is not how long it takes to respond to each individual request, but the rate of requests that our server can handle. And that is called our throughput. So when we talk about concurrency or scaling, when we talk about performance or scalability of concurrency, what we're talking about is throughput. The throughput of concurrent systems is governed by this formula down here, which is called Little's Law. It appears very simple. Actually, deriving it is not so straightforward, but understanding it, I think, is quite simple. So lambda is our throughput. That is the rate of requests that arrive at our system and that we need to handle at the same rate if we don't want them queuing up. W is the average latency for managing those requests. So how long it takes on average to process such a transaction start to finish. And L is what we call our level of concurrency. That is the number of tasks that we have in flight concurrently in the system. So if our throughput is lambda and our latency, average latency is W, then on average, at any single time, our server will need to serve L transactions in flight. If we want to increase our throughput, according to this formula, what we could do is decrease our latency W. But the latency is often beyond our control. And that is because in the course of handling a transaction, we might want to send a request to a different service or a database, and how fast they process that is outside our control. So the other way we can increase our throughput is by increasing L, the level of concurrency, the number of things that our server can manage at the same time. Another way of looking at it is that L, or the level of concurrency, is a bound on how high our throughput can be. And we're going to be talking a lot about that. So in Java, when we speak of concurrency, we speak of threads. And in fact, the entire Java platform is largely built around the concept of threads from top to bottom. At the language level, or the VM level, we have, for example, exceptions. So when we have an error, we get an exception, and that gives us a certain context that helps us debug what the problem is. And that context is the thread's stack trace. We have thread locals that allow us to associate some private thread data. When we debug our application in the debugger and we step through it, we're stepping through the execution of a single thread at a time. When we say step over, it means go to the next instruction on this current thread. If we use a profiler and the current profile for Java, the one that everyone should be using is JFR. It groups the data by thread. It shows us which threads were active, what they were doing, how long they were doing it. So everything about the platform and its tooling is about threads. Threads in Java mean Java-lang thread. That is a class that represents a thread. Currently in OpenJDK, that class has a single implementation. And that implementation is that given to us by the OS. So if we create a Java-lang thread object and we start the thread, what happens is that the Java runtime starts a new OS thread. So Java-lang thread is just a thin wrapper around an OS thread. Now OS threads, they don't know anything about Java, and they need to support all languages, right? Java, C, Python, others. And because of that, they need to be very general. And they don't know exactly how each of those languages and runtimes make use of the stacks. And that means that they have to allocate fixed size stacks that are very big. Also, context switching between threads has to go through the kernel, which is often relatively slow. Finally, the algorithm that determines when a certain thread executes on which CPU core has to be, so the scheduling algorithm has to be some compromise between different kinds of behaviors. So threads can behave in many different ways. A thread that processes transactions going into web servers obviously behaves very differently from a thread that, say, encodes a video. And yet the OS scheduler needs to be general and to be sort of a compromise that's not optimal for any of these use cases. When we use threads to write a concurrent application, we normally, so one option, which we normally do, is we program in a style called synchronous. The synchronous style means that every transaction we process, every task we do, executes start to finish on a single thread. That code is easy to read. It fits with the design of the language and the design of all the tooling and the platform. I say that this is harmonious with the entire platform and its tooling. But because every thread currently wraps an OS thread, and an OS thread is costly, we can't have that many threads at any one time. And because every transaction consumes a thread, the maximum number of threads that we can handle is the maximum number of transactions we can handle at one time. And that is L, our level of concurrency. Modern servers can support about 1 million open sockets, but only a couple of thousand of active threads. So because threads are so costly, they become a bottleneck and they reduce our level of concurrency, which can have a big impact on our throughput. So what do? We say threads are expensive, and as usual, when we have an expensive resource, we try to share it and reuse it. So we use thread pools. What's the idea? Instead of spawning an entirely new thread for every incoming request, we have a pool of threads that we might spawn at the beginning of the application. It stays active all the way to the end. And every time we get a transaction, we borrow a thread from the pool. We run the entire transaction in that thread, and then we return it to the pool. So this gives us some level of sharing, but it already introduces a few problems. So suppose one of the transactions takes a thread and sets a thread local. And for some reason, it forgets to reset it. A different transaction, an independent and unrelated one, will then share the same thread, and it will read those unrelated values of the thread locals, and that's bad. Another problem this introduces is suppose we want to cancel a running transaction for some reason, say it's been running for too long. In order to cancel it, if it's waiting on some IO, we need to interrupt the thread that's running it. But because now we no longer have, because now threads can be shared among different transactions, different tasks, by the time we interrupt the thread that's executing that transaction, it's possible that that transaction is terminated and it's now executing a different one. And that is the one we're going to interrupt. And this makes the entire interruption mechanism quite complex. And this is, in fact, something that we as users need to think about. But that's not the whole story, because even this, with all of its problems, is not enough. In this model, even though we use a pool, we run the transaction start to finish on the same thread. And this means that it consumes a thread for its entire duration. So still, the number of transactions we can have in flight at the same time, that L, that level of concurrency, is still bounded by the number of threads that the OS can support, which is lower than we'd like. So what we do is say this. Okay, so we notice that every transaction, while it's being processed, only a small amount of the time it's actually doing computation on the CPU. Part of the time, it could be waiting for I/O from, it could be doing a client HTTP request to a different service, or waiting on JDBC from a database. So you say during that time, we don't actually need the thread. So what if, while we wait for I/O, we return the thread to the pool, and in that case, some other transaction could reuse that thread before the original transaction is terminated. And this, in fact, allows us to have many more transactions in flight than we have threads, right? Because while a transaction is running, if it's waiting, we say, okay, we release the thread, we return it to the pool, it can be reused by a different transaction, and then the original transaction takes another thread only when that I/O operation has completed. The problem with that is that the ordinary design of the platform, the ordinary APIs no longer work, because they block and they hold on to the thread while they wait. So we need to use a different kind of APIs that are incompatible with the regular ones. Also, we no longer have any sort of, even a temporary association between a transaction and a thread, because we need to chop down the transaction into tiny pieces, tiny stages, and between which we want to return the thread to the pool. And when the next stage executes, it could be the next stage of the transaction, it could be in an entirely different thread. And once we no longer have this association between a transaction and a thread, we lose that context, because a Java platform gives us context through a thread. So if we have an exception, the stack trace will not show us the relevant stack trace for that transaction, only for that small stage of it. If we try to debug it and we want to perform the next step, it's not going to be the next step for the transaction. It's going to be the next step for the thread, which could be executing a different transaction. If we try to profile it, we hardly see anything, right? Because it's possible that we have many transactions that are running, waiting for some I/O, but because they're waiting, they've returned their threads to the pool, and the profile would just tell us that thread pool is idle, and we'll have no idea what each transaction was doing and for how long. In any event, this kind of programming, this style of programming, is called asynchronous. On the plus side, it's scalable. The number of transactions we can handle at any one time is no longer bounded by the number of threads we can have. But it's hard to read, hard to write, and we lose that important context. So we make good use of our hardware resources, but our application is much harder to write and maintain. And this means that developers are facing a dilemma. They can either write simple code, but then their use of hardware is wasteful and they need to spend more money on hardware. Or they say, we want to make good use of the hardware, but then they need to manage an application that is asynchronous and is hard to develop and maintain and profile, et cetera, and that means that they have to pay more money for development. So either you waste more money on hardware or more money on development. How do we break this dilemma? What if we could lower the cost of threads? If we could have threads in Java, but more of them, we won't have this dilemma anymore, right? If we could have an unlimited number of threads, then we could write the same synchronous code that's going to be harmonious with the platform. But because we have many threads, we can make use of the full resources of the hardware. So we'll get code that is easy and easy to maintain and harmonious with the platform like synchronous code, but one that scales like asynchronous code. And that is what Loom is about. So the Java architects gave us the task of rethinking threads. Whenever we want to introduce a new feature to Java, we have to do sort of a balancing act. we need to balance conservation and innovation. By that we mean that it is desirable that new features are forward compatible. That means that old code can benefit from them. A good example of that is lambdas. Right, so if you had old pre-Java 8 code that made use of, say, the runnable or callable interfaces, then automatically starting Java 8, you were able to pass a lambda to that code. So that is called forward compatibility, and it's very nice to have. On the other hand, if we introduce something new, it's an opportunity for us to fix past mistakes. Over the years, the Thread API has accumulated a lot of craft, a lot of methods that are no longer used today. In fact, I was surprised to realize that there are some methods on Thread that I'd never used before and never even knew existed. And if we could start from something new altogether, something new and clean, it might be easier for new developers to learn how to use it. And so we examined how threads are actually used in existing code today. And we discovered that different aspects of the API is used differently. So thread current thread and thread locals, so that part of the API is actually very pervasive. If the new kind of thread, the new lightweight kind of thread, the threads you can have as many as you like of, if they didn't support these two and with the same behavior, then there would be very little existing code that we could actually run. On the other hand, much of the other parts of the Thread API are hard to use at all. Most code today doesn't even call the thread constructor. It doesn't call thread start or thread join, and many of the other methods, some of which you might have never heard of. Instead, starting with Java 5, we've encouraged people to use the Java util concurrent, execute, and future interfaces. And that is how most people write threaded code. So even if we were to keep the existing Thread API, its baggage doesn't really impact new developers too much because they don't really use it, most of it. Also, we have a new policy regarding deprecation removal, and we realized that over time, we could gradually remove some of those rarely used old methods on threads that were a mistake. And the thread class itself doesn't really add a lot in the way of footprint. So we decided to keep the Java-lang thread. And in addition to today's platform threads, so a platform thread is a Java thread that just wraps an OS thread, we introduce a new kind of thread. And that one is not a wrapper of an OS resource. Rather, it is a kind of thread that is implemented by the Java runtime. And the Java runtime can support many more threads, and they can make those threads much more lightweight than the OS. Why? For one, it knows about Java, right? It knows how Java code makes use of the stack. This means that instead of allocating a huge chunk of memory for the stack, we can have a stack that dynamically grows and shrinks. The OS can't do that because the OS doesn't know how Java uses a stack. The context switching is done in user mode, which is faster than through the kernel. And when it comes to the choice of scheduler, I said that normally the OS gives us some sort of compromise. It's possible even to pick the right scheduler for your use case. But mostly the biggest benefit is that memory usage is much slower, so we can have many more of these. And we call these virtual threads. The OS takes the threads and schedules them directly on CPU calls. The Java runtime doesn't have direct access to the hardware. So instead, we simulate the CPU calls by scheduling the virtual threads on top of a small number of OS threads, which we call carriers. So if we take a look back, it's kind of going back in time a bit. If you look back to Java's early days, before 1.1, I think, at the beginning, the first Sun Microsystems JDK, we also had threads implemented by the Java runtime in user mode that we called green threads. Green threads were actually scheduled onto a single OS thread, so they were single call only. Since then, until today, we have those platform threads, which are one-to-one wrappers of OS threads, And Loom introduces, it doesn't take away platform threads. In addition to those, it adds virtual threads that schedules a great many virtual lightweight threads onto a small number of OS threads. So how do we do? If a platform thread on the left here, in terms of footprint, it requires about 2 kilobytes of metadata and about 1 megabyte of stack by default. Context switching can be more than 1 microsecond. If we look at virtual threads, they only require a couple of 100 bytes of metadata, and the stack is pay as you go. It grows and shrinks. That's the biggest advantage. And task switching is also much faster. That's a bonus. So thanks to this, we can essentially have as many threads as we like and have that level of concurrency grow and not be bound on our throughput anymore. How do we use those virtual threads? So we use them just like normal threads, but we need to create them differently. So when we create a thread, we need to tell which implementation we want, whether we want a virtual thread or a platform thread. So the easiest thing is we have this helper class. This is in the current Loom prototype. This is all subject to change. We can just start a virtual thread, give it a task, it will execute it just like any thread. We've also added a builder API on top of thread that allows us to configure threads before we create them. So if we want to create a virtual thread, we create a builder, we configure it to be virtual, and then we can either just build it or build it and start it. And one very nice thing we can do is instead of building a single thread at a time, we create a thread factory that is an existing interface that is commonly used by many executors today. So this factory would create, generate virtual threads, and we can pass this factory to any existing executors that use the thread factory to create their threads. So it seems that all we're doing is just adding another more scalable implementation of threads, or downsizing threads. But sometimes downsizing has a big impact on how things are used. So we can think of a smartphone as a downsized mainframe, but because it is downsized, it has completely different uses than that of mainframe. So threads that are lightweight, even though we already know how to use them, the ramifications are that we can write code in a different way. We don't need to pool threads anymore, right? We pool things when they are costly. Once threads are not costly, virtual threads are very cheap. We don't need to pool them. So every incoming request, we just create a new thread for it. What if that, in the course of processing the transaction, we want to make multiple calls to multiple microservices and a database and do all that concurrently? Not a problem. For each of those calls, we just spawn a new thread. It's cheap. So the code becomes quite different just by virtue of these virtual threads being more lightweight. Nevertheless, because now we will write code with many more threads, we thought it might be a good idea to help people manage this large number of threads. And we found this idea elsewhere. It's called structured concurrency. The term was coined by Martin Sustrick. There's a great explanation of it in these 2 blog posts by Nathaniel J. Smith that I'd recommend everyone read. I think they're brilliant. And this is something we've decided to adopt, at least in the current prototype, to see how it works. The general idea behind structured concurrency is that if we have some sequential process over here that then splits into multiple things we want to do concurrently, we don't continue in the original process until those multiple threads that we created terminate and we join back again, right? So every time we split, we need to join before we can continue. Let me give you an example of something that's not unstructured concurrency. So if you call a method and that method spawns a new thread and returns, and that thread continues running in the background, so that's unstructured, right? It's fire and forget. It's still running there in the background. You don't know how long it's going to live. No one's in charge. That's unstructured. Structured means that the runtime behavior of the program, in this case, the lifetime of the threads, is mirrored in the structure of the code. When you look at the code, you're able to tell when each thread begins and ends. And let's see what it looks like in Java. So there's a shortcut for doing this. I'll show it to you later, but for now I want to show you the long form. So say we have this thread factory that creates, that's configured to create virtual threads. And we pass it to an executor. I'll go back to this executor in a moment. This executor, whenever it wants to create a thread, it will use that factory and it will use a virtual thread. And then we submit it tasks. Okay, this is a new kind of executor. It's called a thread executor, and it's a very simple one. It doesn't pull threads at all. Every task you submit to it, it will spawn and create and spawn a new thread for it. And because we've told it to use virtual threads, each of those tasks will execute in its own, virtual thread. Now, what is this business with the try with the resources block? So in Project Loom, we've changed the executor service interface that's returned here to extend auto-closable. This allows us to use this inside a try with resources block. And a try with resources will automatically emit a call to the close method when we reach this closing brace. And the close method on an executor in Project Loom will just wait until all the tasks in that executor have terminated. In this case, each of those tasks has its own thread, so it will just wait for those threads to terminate. So let's see what happens. You submit a task, it is a new thread executor, so it will create a new thread. It will do that by calling the factory. The factory is configured to use a virtual thread, so this creates a new virtual thread, this creates another, and we have two virtual threads. And then we reach the close braces, we call with the close method, automatically it's implicit here, and then we wait for those to terminate. So we can't continue, we can't exit this block until those two threads have terminated. So this is structured. They're born here, they die here. What does this give us? It actually has some cool implications. One of the things we often do in servers is we, in some cases, we must cancel some operations. Say we want to do some IO call to another service and it's taking too long and we want to cancel it. So we start working with timeouts. But then we might want to retry some things, and the combination of retries and timeouts and deadlines and passing them all through the call stack gets to be quite complicated. But thanks to this, what we do is we configure this entire executor, which, like its threads, it's very, very cheap. Don't be afraid to create it. We just say that it has a deadline of 30 seconds. And then it's going to start these two tasks in their own virtual threads as before, and then it's going to wait for them. But if those threads terminate and those tasks finish before this deadline has lapsed in 30 seconds, then we just continue. If they don't, or one of them doesn't, that thread will be interrupted. Either way, we will still wait for all those threads that were created here to terminate before we continue. That is the guarantee made by structured concurrency. Okay? Okay, now what about results? If we, oftentimes we want to start a thread, get a result and do something with the result. So we have several interesting combinators for managing different kinds of results from multiple threads. This example is called, it uses the Invoke Any method. In this case, we pass Invoke Any list of tasks. Each of them will be submitted to the executor. And in this case, I'm using the shorthand. It says new virtual thread executor. It automatically uses a virtual thread factory. So each of those will be submitted, each of those will run in their own virtual thread. But this Invoke Any says that I only want to wait for the first one that terminates normally, the first one that gives back a result without throwing an exception. And that is what is going to be assigned to first, unless all of them throw an exception, in which case I'll get an exception. We have an analogous method called invoke all if we want to collect all the results. And that, I think, is everything. Once again, the early access builds of Project Loom are here. You could just download them. They are the full JDK with the Loom capabilities in it that you can try, and then send us feedback to this mailing list. And at this time, I think I'll take your questions. Any questions? Okay, which JDK release do you expect Loom to appear in? Okay. So first of all, every new Java feature is now commonly, especially the big ones, is now first introduced in as a preview feature. So it gets introduced into the mainline JDK, into some version, but in order to use it, you have to add certain flags, and the goal of that is to gather feedback from more people who don't use the early access. So Loom will first appear in some version as a preview. We are working towards the first preview. I can't say exactly when, but we're working on getting to a preview. Next question. What kind of feedback do you want from the early access builds? Okay, so you can give us any kind of feedback, but the best kind of feedback is to download the builds, try them, play with them, and then write about your experience to the mailing list. What was good, what was bad, what could be better. That is the best kind of feedback. What can't I do in a virtual thread, whether there are any restrictions? Okay, so that one is interesting. Generally, in terms of the behavior, so a virtual thread behaves just like any ordinary thread. Anything you can do in an ordinary thread, platform thread, you could do in a virtual thread. However, the purpose of virtual threads is to have, like I said, many of them. And for that, they need to be lightweight. And currently, there are some limitations that could limit that scalability. The first one is if you call native code via JNI, that's fine. But if that code blocks, then it will actually block a kernel thread. So you won't get that nice scalability. If it happens from time to time, that's okay. But if it happens very, very frequently, then it could affect your scalability. That limitation will probably never go away. But on the other hand, it's not very common for people to call into JNI and for that code to block, especially in Java. Another restriction, which is more painful today, but I think it is temporary, is if you try to do some I/O operation while you're holding a native monitor, that means while you're inside a synchronized method or a synchronized block, then the actual underlying kernel thread will be blocked as well. This means that today, as long as we have that limitation, and I don't know how long it's going to be, but it's certainly probable that in the first preview of Loom, that limitation is still going to be there. If you are doing any kind of blocking operation today inside a synchronized method of block, and you want to benefit from the full scalability of Loom, replace that synchronized with Java util concurrent blocks. Other uses of synchronized, like I know synchronized maps, those are fine. So if you want to prepare yourself for Loom and you're afraid that limitation might still be, find where you are holding a monitor while doing I/O, replace those with Java util concurrent blocks. Loom has some features that will allow you to detect it at runtime. So if this happens very often and you're afraid it might be harming your throughput, Loom will actually tell you where this happens so you can fix it. And I hope that sooner or later we'll have that restriction go away. Yes, next question. When are ordinary platform threads preferable? I would say that virtual threads are better for transaction processing. Transaction processing is when you have operations that wake up because of some external request, do some processing, maybe send some IO or message to some other thread, and then block again. So they operate in bursts as a response to external stimuli, right? So transaction processing threads, I would choose virtual threads for those. If you have any sort of heavyweight batch processing, CPU-bound, computation-heavy kind of work, and like encoding a video, that is the kind of thing I would do in a platform thread. Next question. You mentioned replacing locks. Is there anything else existing frameworks should do to migrate? What about thread pools? Okay, so we've done nice experiments with Jetty. Jetty is a servlet container, and it allows you to configure its thread pool to use a different executor. So we just replaced its thread pool with that new kind of thread executor that uses virtual threads. And we were able to get much better scaling from Jetty without any other changes. So if your framework has any kind of configuration into various thread pools, just replace those with the new executors that don't pool but use virtual threads. Another thing is that in some libraries, I've seen people try to limit concurrency in certain places by having small thread pools that do, I don't know, that access some external microservice. I would say don't do that. Don't try to use pools for any reason. Instead, wrap the access to those limited resources with semaphores. So then every thread that wants to access them tries to acquire a semaphore and then returns it, then releases it, and then you can limit the size of the semaphore. And that way you could limit the number of threads that are doing some specific operation concurrently, say if you want to limit the number of threads accessing the database. So semaphores are a better way to control concurrency at a finer grain level per resource. Any more questions? Okay, so next up, we have in one room Stuart Marks giving a talk called Collections Refueled. My guess is that it's going to be about collections. And in the other room, we have a panel with some Java architects where you can ask questions. So we have the architects Mark Reinhold and Brian Getz, and also some non-architects like Michael Wittstedt, and I might even join there as well, not sure yet. You can go to the website to look at the agenda and click the join button to join either of those sessions. So thank you very much. Bye-bye.